Hi friends, I'm going to show you some pictures and you need to tell me what is common to the things that you see. So are you ready? Now what is common to an electric bell, this crane lifting iron junk, a maglev train and an MRI machine? That's right, they all work on the magnetic effect of current, or what is called electromagnetism, and that's going to be the topic of this video. We look at the magnetic fields of conductors of different shapes and compare electromagnets and permanent magnets. I'm going to make the concepts really easy for you. And after you watch this video, try solving the quiz and the top 3 questions on this topic. Links are given below the video. I'm sure you're familiar with electricity and what is electric current. You can also watch my video on electricity. Electric current, as we know, is the flow of electric charges. When current is flowing in a wire, the electrons, which are negatively charged particles, are in motion. Electric current has many interesting effects, such as heating effect, chemical effect, and magnetic effect. When current passes through a wire, it heats up the wire. This is called heating effect of electric current. An example of heating effect is a simple bulb. When electric current passes through the bulb, the tungsten filament gets heated up and it glows. Now, do you know what is the chemical effect of electric current? You may have heard of electrolysis. Electric current is passed through a compound to decompose it into simpler substances. For example, electrolysis of water. When electric current is passed through water, it breaks down into hydrogen and oxygen. So electric current causes a chemical reaction here. That's why it's called chemical effect of electric current. In this video, our focus will be on a very interesting effect of electric current, the magnetic effect of current. So let's dive right into it. Magnetism has been known since ancient times, and electricity was discovered in the 1700s. But later in 1820, a scientist by the name of Ørsted discovered a very interesting phenomena. In his experiment, he used a wire and a magnetic compass. Ørsted observed that when the switch is off, no current flows in the wire and the compass points in the regular north-south direction. But when he put the switch to the on position, current flows in the wire and the compass gets deflected from its usual north-south direction. And when the switch is off, the compass comes back to its original north-south position. A magnetic compass is made of a tiny magnet and it can only be deflected by a magnetic field. So Ørsted concluded that when the wire carries electric current, it behaves like a magnet. A current carrying wire creates a magnetic field around it. And this is called the magnetic effect of electric current, or electromagnetism. In other words, electricity is producing magnetism. It's like magic. Previously, electricity and magnetism were treated separately. But now, after Ørsted's experiment, we know that the two are linked. Electricity can produce magnetism. Now, can magnetism produce electricity? What do you think? That's right. The answer is yes. And that's exactly how an electric generator works and produces electricity for us. But we'll discuss that in a separate video. We have learnt that a current carrying conductor produces a magnetic field around it. The pattern of the magnetic field, that is the shape of the magnetic field lines, depends on the shape of the current carrying conductor. We will discuss the magnetic field patterns produced by conductors of different shapes: a straight wire, circular loop, and a solenoid. Let's start with the straight conductor, that is a straight wire. Now, when no current is flowing through the straight wire, there is no magnetic field around it. And when the current flows through the straight wire, it creates a magnetic field around it, which looks something like this. They are concentric circles centered around the wire. Now, to make things simple, let's just consider a single plane that is perpendicular to the wire. As you can see, the magnetic field lines are concentric circles lying on the plane and centered around the wire. How can we know the shape of the magnetic field? That's right, by using iron filings or a magnetic compass to plot the magnetic field lines. As you know that the magnetic field lines have a certain direction. The direction of the magnetic field lines are marked with arrows here. There is a simple rule that can help us determine the direction of the field lines. It's called Maxwell's right-hand thumb rule. I want you to hold up your right hand like this and make the thumb point in the direction of the current. Note that this is the conventional direction of the current. Since the current in the wire is in the upwards direction here, point your thumb upwards. Imagine you're holding the wire with your fingers. Now the direction in which your fingers curl is the direction of the magnetic field. As you can see that the arrows of the magnetic field match the direction in which your fingers curl. The direction of the magnetic field is anti-clockwise. In the right-hand thumb rule, the hand looks like a YouTube or a Facebook like button. Which reminds me, don't forget to hit the like button. Now what happens if we reverse the direction of the current? When the current is downwards, our right hand will look something like this. The direction of the magnetic field will be how our fingers curl. So the magnetic field will be opposite. Magnetic field will be in the clockwise direction. We have learnt that a current carrying wire behaves like a magnet. But have you ever experienced this behavior? For example, when you put your phone on charge, have you ever noticed any iron pins being attracted to the wire of the charger? No. As you can see here, the iron pins don't get attracted to the wire. But when I bring a magnet, it can easily attract the iron pins. Why we don't notice the magnetism for the wire? That's right. It's because the magnetic field created by the wire is very weak. To create a strong magnetic field, a very high amount of current has to be passed through the wire. So the magnetic field is directly proportional to the amount of current in the wire. That's why the magnetic effect of electric current was discovered much later in 1820. Now, do you know how the magnetic field changes based on the distance from the wire? The strength of the magnetic field is inversely proportional to the distance from the wire. So, greater the distance from the wire, the magnetic field will be weaker. Now, let's look at the magnetic field pattern due to a circular loop. If you take a straight wire and bend it into a circle like this, and now when you pass current through the wire, it creates a magnetic field around the wire. The magnetic field of a circular loop is stronger than a straight wire. To understand the magnetic field of a circular loop, imagine that the loop is made up of small segments, which are approximately straight wires. Each of these straight segments produces a magnetic field around it, which is in the shape of concentric circles around the wire. The magnetic field lines are circular near the wire. But as you move away from the wire, the concentric circles become bigger and bigger. At the center of the loop, the magnetic field lines are approximately straight. We can find the direction of the magnetic field lines for each segment of the loop using the right-hand thumb rule. So for each segment, you need to align the thumb so that it points in the direction of the current, and your fingers will give you the direction of the magnetic field. As you can see, the magnetic field lines for all the segments of the circular loop have the same direction at the center of the loop. So all the magnetic field lines will add up at the center of the loop and the magnetic field will be stronger. How can we increase the strength of the magnetic field at the center of the loop? That's right, by increasing the current. The strength of the magnetic field is directly proportional to the current in the circular loop. Now instead of one circular loop, let's say there are 5 circular loops. The wire is turned into 5 turns, that is 5 circles. Now how do you think the magnetic field will change at the center of the loop? That's right, the magnetic field will be stronger. In fact, the magnetic field will be 5 times stronger, since all the magnetic field lines will add up. And if there are n loops, the magnetic field will be n times stronger. The magnetic field is directly proportional to the number of turns of the wire. A current carrying circular wire behaves like a thin disc magnet. A disc magnet looks like this. Can you see it attracting the iron clips? Where are disc magnets used? You might have seen them being used for fridge magnets. So if you flip the fridge magnet, you can see the disc magnet at the back. Now just like a coin has one side heads and the other side tails, similarly one side of the disc is the north pole and the other side is the south pole. So one side of our current carrying circular loop is the north pole and the other side is the south pole. But how do we know which side is the north and which side is the south pole? We can use the clock face rule to find the polarity. The clock face rule says that if you are looking at the face of the circular loop and the current is flowing in the clockwise direction as shown here, then it is the south pole. And if you are looking at the circular loop and the current is flowing in the anti-clockwise direction as shown here, then it is the north pole. An easy way to remember this is anti-clockwise has the letter N in it. So it is the north pole and clockwise direction will be the opposite pole, the south pole. Now if you look at the loop here, as you can see, for us the current is in the clockwise direction. So this side of the loop is the south pole. And now if I go back and look at the loop from behind, then the current will be in the anti-clockwise direction for me. So the back part of the loop will be the north pole, the opposite pole as expected. Next, let's look at the magnetic field due to a conductor of a different shape, a solenoid. A solenoid looks like a spring. It is a long coil made of insulated copper wire containing a large number of turns. Now when electric current is passed through the wire, each of the turns in the solenoid is a current carrying circular loop. So each circular loop is producing a magnetic field around it. The magnetic field of all these turns add up to produce a strong magnetic field of the solenoid. Now what is the shape of this magnetic field? Can you see that the magnetic field of the solenoid is similar to the magnetic field produced by a bar magnet? A bar magnet has 2 poles, north pole and south pole at the 2 ends of the magnet. Now how do we determine which end of this solenoid is the north pole and which end is the south pole? The solenoid is made up of many circular loops and we had used the clock face rule for the circular current carrying wire. So we can use the clock face rule again for this solenoid. Now let's say if you are standing here like me and looking at this end of the solenoid, what is the direction of the current for you? That's right, the current is in the clockwise direction. So if we apply the clock face rule, what pole will be this end of the solenoid? That's right, it's going to be the south pole. Now if I move to the other end of the solenoid and look at the solenoid from this direction, the current is now in the anti-clockwise direction for me. So this end is the north pole. We can use the clock face rule to determine the polarity of the solenoid. The polarity of the solenoid can also be checked using a magnetic compass or another bar magnet. For example, if you bring the north pole of the bar magnet near the north pole of the solenoid, then the two will repel each other, since like poles repel. And if you bring the north pole of the bar magnet near the south pole of the solenoid, then they will get attracted towards each other. We have discussed the pattern of the magnetic field lines outside the solenoid. Now, what is the pattern of the magnetic field lines inside the solenoid? If you look at the diagram, this indicates that the strength of the magnetic field is same at all points in the solenoid. This is called a uniform magnetic field. So the magnetic field inside a solenoid is a uniform magnetic field, and the magnetic field outside the solenoid resembles the magnetic field of a bar magnet. Let's place the magnetic field due to a straight wire on our concept board. The magnetic field lines are concentric circles centered around the wire. Let's pin the magnetic field for a circular loop on our concept board. Let's place the magnetic field due to a solenoid on our concept board. Outside the solenoid, the magnetic field lines resemble the magnetic field of a bar magnet. And inside the solenoid, the magnetic field lines are straight and parallel, indicating that it's a uniform magnetic field. How can we change the strength of the magnetic field of a solenoid? One simple way is to increase the strength of the current flowing in the solenoid. Larger the current in the solenoid, stronger will be the magnetic field. Another way is to increase the number of turns in the solenoid. Larger the number of turns, again stronger will be the magnetic field. We can also place a soft iron rod as the core in the solenoid. Soft iron has the property to get magnetized easily, and it increases the strength of the magnetic field. And this combination of a solenoid and a soft iron core is called an electromagnet. Electromagnets are different from permanent magnets. Permanent magnets are the regular magnets that are used in fridge magnets, toys, microphones, loudspeakers, and other devices. Permanent magnets are made of steel. Usually alloys such as carbon steel, chromium steel, or alnico, which is an alloy of aluminium, nickel, cobalt, and iron, are used. Since permanent magnets made of these are stronger than ordinary steel. And we know electromagnets are made using a long insulated copper wire that is wrapped around a soft iron core. Current is passed through the copper wire. Electromagnets have various applications such as electric bell, a crane lifting iron junk, in a maglev train, or in an MRI machine. Let's go ahead and look at the differences between a permanent magnet and an electromagnet. First difference is, for a permanent magnet, the magnetism is permanent. It doesn't lose the magnetism. Only if it is damaged and beaten, it may lose its magnetism. But an electromagnet is a temporary magnet. As long as the current is flowing through the solenoid, the magnetism is there. But when the current is switched off, the electromagnet is no longer a magnet. And this is a big advantage of the electromagnet. Its magnetism can be switched on and off. The second difference is that the strength of a permanent magnet is relatively low. But an electromagnet can produce a very strong magnetic field. The third difference is the strength of a permanent magnet cannot be changed. But the strength of an electromagnet can be changed by changing the amount of current or the number of turns in the coil. And the fourth difference is that the north-south polarity of a permanent magnet is fixed. It cannot be changed. But the polarity of an electromagnet can be changed. Do you know how? That's right, by changing the direction of the current flowing in the solenoid. Let's place the comparison of permanent magnets and electromagnets on our concept board. I hope the concept of electromagnetism is super clear to you now. We learnt about the magnetic field produced by conductors of various shapes and the rules such as clock face rule and the right hand thumb rule. To revise the concepts, I would encourage you to go to my website and try the quiz and the top 3 questions for this video. To make it easy, I'll put the links below. So just go and click on the link and write your answers for the top 3 questions, and I promise to reply to them as soon as possible. And if you haven't subscribed to my YouTube channel already, go hit the subscribe button right now. You can check my Facebook page and do check out my website manochaacademy.com for more videos like these and for the quiz and the top 3 questions on this video. Thanks for watching.